Section: Introduction. In this section, we will discuss the concept of large language models, LLMs, and the challenges they face, such as the reversal curse. LLMs like GPT-4 and Llama 2.2 have vast knowledge but struggle with reversing facts they have learned. This means they may not be able to answer questions like, "What's the capital of France?" correctly, even if they have been trained on the fact that Paris is the capital of France. This limitation is significant because it hinders their ability to understand relationships like A is the capital of B is the same as B's capital is A. Human children can easily grasp such concepts with minimal exposure, unlike LLMs. The reversal curse was not immediately apparent because most LLMs are trained on large datasets that likely include common facts in both directions. However, due to Zipf's law, many facts are mentioned infrequently or only in one direction, which can lead to gaps in the model's knowledge. To address the reversal curse, we propose a simple training method called reverse training. LLMs are typically trained from left to right, but we suggest training them in the opposite direction as well. This approach allows the model to see facts in reverse, potentially overcoming the limitations of the reversal curse. We explore different types of reversals, such as token reversal, word reversal, entity-preserving reversal, and random segment reversal, to enhance the model's understanding. Our experiments show that entity-preserving and random segment reverse training can help mitigate the reversal curse and improve performance on various tasks. By training in both directions, LLMs can leverage knowledge from different sources and enhance their language modeling abilities. Reverse training offers a promising solution to the challenges posed by the reversal curse and can be beneficial in improving the overall performance of language models. Section Summary. In this section, we introduce the concept of the reversal curse in large language models, LLMs, such as GPT-4 and Llama 2.2, which struggle with reversing learned facts. This limitation hinders their ability to understand equivalences like A is the capital of B equals B's capital is A, unlike human intelligence. To address this, we propose reverse training methods like entity-preserving and random segment reversal, which show promise in mitigating the reversal curse and improving model performance on various tasks. Section: Experiments. In this section, we created a simple symbol-based toy dataset to study the reversal curse in a controlled manner. We paired entities randomly in a one-to-one manner, with training data containing all forward mappings and only half of the backward mappings. The remaining backward mappings were used as test data. To succeed in this task, a model needed to learn the rule from the training data and apply it to the test data. The entity names were made up of random code words, such as two-word entities like A12A64 and B54B42. We used word tokenization for evaluation, where we measured the accuracy of matching the target entity over 3 random seeds. The results showed that standard language model training failed on this task, while reverse_word training almost solved it for 2-word entities but struggled as the entities became longer. Reverse_entity training, on the other hand, performed perfectly even for 5-word entities because it maintained the word ordering within each entity. Reverse_rand could also solve the task, but only when the maximum segment length was long enough. When we applied the reversal curse to a biography dataset of 100K individuals with unique English names, we found that accuracies became non-trivial only in the entity-preserving reversal case for determining the person's full name. Token and word reversals failed in these tasks. When trying to determine a person's full name given only the birth date, the accuracy remained low because dates were treated as separate entities, disrupting their ordering in the reversal process. Simplifying the task to determining the person's last name showed that word-level reversal was sufficient, and token-level reversal also yielded non-trivial accuracies. It was interesting to note that an entity-preserving method could determine the full name but not the last name of a person. This phenomenon highlighted the importance of maintaining the order of tokens in a sequence. Entity-preserving reversals did not affect the model's performance in forward tasks. Mixed training, where instruction tuning data was added to the pre-training level, generally outperformed first pre-training the model with knowledge and then fine-tuning it for reversal tasks. Section Summary. In this section, we conduct experiments on symbolic reverse tasks using a toy dataset where entities are paired in a one-to-one manner, testing the ability of models to infer and generalize rules from training data. We observe that while standard language model training fails, reverse_word training performs well for two-word entities but struggles with longer entities, highlighting the importance of entity-preserving training methods. Additionally, in the reversal QA task using biography datasets, we find that entity-preserving reversals outperform token and word reversals in determining full names, showcasing the significance of preserving entity order in such tasks. Section: Reversing real-world knowledge via pre-training. In this section, we tested our method on a realistic setup by pre-training language models and evaluating their performance on forward and reverse facts about real-world knowledge. We decided to assess our reverse training during the pre-training stage since language models acquire most of their world knowledge at this point. To keep the experiments manageable, we trained a Llama 2 model with 1.4 billion parameters. The baseline model was trained on 2 trillion tokens in the left-to-right direction. For reverse training, we used only half of these tokens, 1 trillion, but trained the model in both the standard left-to-right direction and the right-to-left, reverse direction using the same subset of data. This means that the model received updates over a total of 2 trillion tokens, with 1 trillion tokens processed in each direction. We called this setup compute matched because both models processed the same total number of tokens and used the same computational resources. We also compared it against a data-matched baseline trained on 1 trillion tokens in the standard left-to-right direction. This baseline model had half as many updates but had seen the same data examples as the reverse-trained model, albeit only in one direction. For reverse training, we used entity-preserving reversal for 5% of the pre-trained data, while the rest used word reversal due to the higher computational cost of the entity reversal procedure. We also tested other reversal mechanisms in our experiments. To evaluate the reversal capability on real-world facts, we used a celebrity task with challenging questions like, the mother of celebrity_name is, and even more challenging reverse questions like, the child of parent_of_celebrity is. We conducted a 2-shot evaluation using our pre-trained models without any fine-tuning on this dataset. The accuracy was generally low due to the small model size, limited pre-training, and lack of fine-tuning for both baselines and our method. However, in the forward direction questions, the reverse training performed better than the data-matched baseline, indicating that reverse training can be beneficial even for standard tasks in data-bound scenarios. In the compute-matched case, where the baseline had access to more data, reverse training slightly lagged behind for 5-10 samples. Importantly, in both the data-matched and compute-matched cases, we observed significant improvement in the reverse direction questions for reverse training compared to either baseline. This shows that employing reverse training during the pre-training stage can help make the model robust against the reversal curse. We then investigated if our reverse training could be applied during the fine-tuning stage when the model learns new, previously unseen knowledge from a small training dataset. We used the same pre-trained models and an additional Llama 2 7B model, and further fine-tuned them on a dataset consisting of fictitious facts. These facts were statements like, name, is, description, or the reverse, where the names and descriptions were randomly generated. Since these facts were not seen during pre-training and were only encountered in a specific direction during fine-tuning, we tested if the model could learn them in the same or reverse direction. The evaluation results for different pre-training and fine-tuning setups are provided in a table. We used a soft matching score as the test accuracy, evaluating the exact presence of the target sequence in the first 64 tokens of the model's prediction. Across all pre-trained models, fine-tuning with reverse training was crucial for solving the reversal of name to description, achieving close to 100% accuracy for the larger 7B model, while standard fine-tuning always resulted in 0% accuracy. For reversing description to name, only fine-tuning with the random segment reversal succeeded, reaching an accuracy of around 70%. This is likely because generating descriptions is more challenging due to their length and variability. We observed some improvement from reverse pre-training in the data-matched case but not in the compute-matched case, which was expected since the evaluation statements were fictitious and not present in the pre-training data. Section Summary. In this section, we explore reversing real-world knowledge through pre-training by evaluating language models on forward and reverse facts. We train a Llama 2 model with 1.4 billion parameters using reverse training, which shows improved performance on reverse direction questions compared to standard baselines. Additionally, we investigate reversing fictitious facts during the fine-tuning stage, where reverse training proves critical in solving the reversal of name to description statements, achieving close to 100% accuracy for larger models. Section. Does reversal training hurt performance on standard tasks? In this section, we explored if our method disrupts zero-shot performance on common evaluation tasks such as Bool Q, PIQA, SIQA, Hella Swag, Wino Grande, Arc Easy and Challenge, Open Book QA. We also looked at 5-shot performance on the aggregated MMLU benchmark. Our evaluation results showed that our entity reversal trained model performs slightly better than the standard data matched 1.4B model trained in the standard forward direction. It is only 1.8 points behind the compute matched model in accuracy on average, even though it was trained on half of the tokens. We found that token reversal works slightly better than entity reversal on these standard benchmarks and is superior to the data matched standard training. Additionally, we discovered that reversed models can generate text continuations in the normal left to right direction and can also generate the beginning of the text given a continuation, a capability that standard models lack. To understand the effect of segment granularity when reversing sequences, we evaluated the performance of different training methods on the fictitious celebrities task. We found that reversing at a fine-grained level, such as token or word level, does not significantly help to resolve the reversal curse and only improves performance on the reverse tasks by 2 to 3%. Preserving entities during reversal makes it possible to predict names but not descriptions, indicating a close relationship between the unit of reversal training and the target concepts of the reversal task. Random segment reversal performs poorly at predicting descriptions when the segment length limit is set lower than the typical length of a description. The reversal curse was identified in previous works and occurs across model sizes and families, including very large models like GPT-3.5 and GPT-4. Including auxiliary examples with both orders present in the fine-tuning or pre-training datasets does not aid generalization to examples where only one order is given. Augmentation during the pre-training phase is essential for enhancing downstream question answering performance across various tasks. Reverse training presents a distinct language task to the language model, avoiding interference with the primary task of left-to-right natural language modeling. Various methods have been proposed to address the reversal curse, including training right-to-left, masked language models, and other training variants. Our work aims to rectify the issue while keeping standard language model training as similar as possible to the current regime.